up on this. Last time I did a really bad version of population distribution, so I've learned my mistake and I'm not doing that again. But let's basically, we're going to use SALT to find the percentage bigger or less than or equal to anything. So suppose I have a population and that the mean height of adults is, say, 60 inches, and that the standard deviation is 3 inches. With that information and the fact that I'm told that it's a normal distribution, I can essentially find any percentage of any kind of number I like. I can, for instance, find what percentage or what proportion of people are bigger than 62 inches. I can find what proportion of people are less than, say, 50 inches. I can find what proportion of people are between 58, for no particular reason, 72 inches. And all of these and any other combination you like, any other numbers, can all be done using SALT. So essentially what you do is you go into SALT, you tell it it's a normal distribution with these parameters, the mean and standard deviation. And then you do one of these three fellas. Now, I'm going to go to SALT and do this in a minute. But remember, I think it was little circles or something that they had, didn't they? And you picked. If you wanted to get the percentage of people whose height was bigger than 16, was it a right-tailed or a left-tailed or a between? I think that's what they called it, right, left, or between. Which one do you use for that?
Is it right tail?
Yeah. So you choose, let's say that one's the right one. And this one is a left. And this one is a between. I'm not saying that's the order. So keep that thought and let's go and see how we would actually simply get SALT to do this. I've already mentioned that test 3 is going to be pretty much in WebAssign because of you're going to be using SALT for all sorts of questions. So I'm just going to use this tab. There we go. Hopefully you're looking at the SALT menu, right? You're inside it. Is that what you're saying? Okay, good. So, boom, boom, there we go. Now, normal distribution, check. In this country, the average height was 6 inches and the standard deviation was 3. And I want, the first one I wanted was bigger than or equal to 62, right-tailed, bigger than or equal to 62. Can you imagine in a homework situation or in a test situation, all I will get is the final answer here. So you have to be really careful because I can't give you partial credit if you typed in 26 when you meant to type in 62 or something. So just be careful. And isn't the answer we want that guy down there? And as a decimal, the answer to that one, let's say 3 decimal places, is 252. Now, the second one I had was what percentage of people from this country are less than 50 inches tall? So left tail, 50 inches. And the answer is, maybe not surprising, is very, very small. It's 0.1230 zeros and say a 43. And the between, was called between, good. So if you want to do a between, it was what percentage of the population are between 58 inches and 72 inches. And in this case, the answer is a big chunk of people. It's 0.74, to 3 decimal places, 747. Would you agree that intuitively SALT is pretty clear what you need to do to get the answers that you're looking for, right? Just leave that as normal. I can't see a reason why you want to change that. Put in the mean and standard deviation, and depends on left, right, or both. Right?
Vienna's
Which
in
letter
the
between.
waiting room.
Thank you. I'll let her in. So far, so good. Right. Let's see if this is going to work. No, it's not going to work. Let me stop sharing for a minute. Here we go. Are you looking at question 10 from homework? Oh God, I'm getting good at these windows today. I'll make this a little bit bigger because I know some of your screens are quite small. Okay. So this one is what I called applications yesterday. So basically we're just going to get a story. And then in this story, they're going to ask you to find, if you chose one day at random, or if you want to phrase it differently, what percentage of the days would be less than or more than something. So suppose the yearly rainfall totals for some city follows a normal distribution, which is nice. The mean is 24. The standard deviation is 10. So I'll just write that down because I'll forget. So the mean is 24 and the standard deviation is 10. For a randomly selected year, what's the probability that the total rainfall will fall in these regions? So you want less than 10, bigger than 49, between these two numbers, or 59, right? And I've got those darn answers on again, but I guess that way I can check I did it right. Okay, suppose you want to know, okay, what percentage of the years would you get less than 10 inches? So you hit salt. Going to stop sharing for a second. Okay, hopefully you're looking at the salt menu. Move all my little windows around. And I'll shrink this back. There. Okay, so hopefully you're seeing the salt window. And what I'm going to do is, in this story, the mean was 24. And the standard deviation was 3. And the first question was less than 10 inches, right? So if it's less than 10 inches, oh, left tail for less, right tail for more, right? So it's less than 10 inches.
I feel like the standard deviation was 10.
It was.
Okay.
Thank you. I wrote it down and then I just ignored what I wrote down. Go figure. So that'll probably explain why it was having a hiccup a minute ago. So less than 10. And there's that 0.0808. So if you round this off to 4 decimal places, it matches exactly the one that they've got here. Now, if you want greater than, it was what, greater than 49, you click on here, you type in 49, and the answer you're going to write is that one, which, well, they've called it 62, so I'm wondering if there's an extra digit after that. No, it is 62, I take it back. And you can do a between, and you can do a greater than, all the good stuff. I think it's pretty much what you see is what you get. Agreed? You know, you just type it in and, you know, the rest follows. Question 11 is about the heights of people. Oh, okay, let's do question 10. I'll just read it out to you. These are for the nursing kind of medical people that might be interested in this story. In question 12, the total cholesterol level for women aged 30 to 39, well, that's very specific, has a mean of 204. So I'm just drawing, let me show you what I'm doing. So did you know that women between 30 to 39 have a cholesterol level which is normally distributed, and that the mean is 204, so that would be about here, and that the standard deviation for such people, such women in that age group, is 37. And it says here, find the cholesterol level. Find the cholesterol level. % of the women. Have a value that's that or less. So can you imagine there's a guy over here, so that 19% is there. And we're actually going to be finding that number, which isn't, don't we normally know what this number is and we find out it's 19%. But now you're going to do a 19% and find out what this number is. So I'm about to go back in and do a salt on that. And we'll show you how you adapt the SALT program to take account of this new situation. So here is the SALT window. Usual question, are you seeing it? Can you see the normal distribution? No, okay. So that's why I keep asking things that are obvious, because sometimes they're not. Can you see it now? Can you see the SALT window with the normal distribution? Okay, what are you gonna do this time? Third time lucky. Can you see it now? Don't ask me what I just did, because I couldn't repeat it if I did. But evidently I hit the right window instead of whatever the wrong window is. So we have got this one. And that's annoying. No. Okay, I've got you along my bottom window. Can you see yourself? Or can you just see the salt? Do you see little pictures of yourself?
I just see salt.
Okay, we're just gonna, yeah, we're just the salt, good. Right, so back into this storyline. The cholesterol had a number that was 200 and, oh God, is it 4 or 6? I can't read one right.
4.
Let's call it 204, all right. And the standard deviation was 37. Well, that's good. It's a left tail story, so that's good. Normally we put a number in here and we read off the probability. All you do is put the probability there and read off the number. You see, it's just a matter of putting the 19% here, and the guy that they're wanting is about 172 if you round it off to the nearest whole number. So I'm going to use this since it's already set up. Let's suppose that we consider an unhealthy cholesterol level if it's in the bottom 10%, right, of the normal distribution, right? If you're kind of low, you're in the bottom 10%. So what we would do is we'd go here and we'd make that 10. And now the doctor has a number. If your cholesterol level comes in at, say, 156, you are going to have, you know, if you've ever done blood tests, you'll know what I'm talking about. You get a report and it tells you your number. And then sometimes it says normal, high, or low, or something, right? So in this case, you would be, if you came out with a cholesterol level of 156, you would be in the low. And your doctor would be looking at you and thinking, is there a problem here, right? Because you want to know what's a normal kind of range, right? Nothing's going on here, nothing to see, keep moving, and an extremely low value, right? So 10% would be something that person would be concerned about. Maybe it's just you, maybe you body chemistry is like that. On the other hand, if you were in the bottom 1%, let's make that a 1%. If you are in the bottom 1%, which would be a cholesterol level of what, about 118, wouldn't that probably be, your blood work has just came back. I want you to come in. We need to talk. Because that probably is an indication of something very serious, right? If you're in the bottom 1%, you've probably got something going on with your cholesterol. Now, I don't know if low cholesterol is as bad as high cholesterol. So let's do a right-tailed. And a high cholesterol is 290. So you are in the top 1% if you're a woman in that age range. And I believe, not being a medical person, isn't high cholesterol related to bad things like heart disease and so on? For the medical people amongst you, you might agree with that. But can you see how useful it is to have this process that, as long as it's normally distributed, you can find what percentage of people have a cholesterol bigger than 100, less than 92. What cholesterol level do you need to be in the top 2% or the bottom 10%? I think that's a very helpful thing to be able to do. And I would make the assumption that when I get my blood work, someone has already decided what number is considered high and what number is dangerously high. And this is just me being curious. Does anybody here is going to go into the nursing program? Right. Liana, have you done anything where they talk about blood pressures and cholesterol levels? Have they done things like that yet? Or do you know that you're going to eventually do things like that?
I know that I'm eventually going to do things like that because, like you said, they do tell you if you have any underlying health problems, but I haven't actually started studying it yet.
Can you see where these numbers are going to come from then? How they decide what is what is an extremely high cholesterol level, right? And what's an extremely low cholesterol? And now you could replace that, couldn't you, with blood pressure, body mass index, potassium level, iron level. I mean, you could go through all the things that they check on your blood, right? What's the one for infection? I think if you have a high white blood cell count, isn't that a very good sign that you've got an infection going on? Because your body tends to produce a lot of white blood cells. And so there'll be a range that you normally have, and then there'll be a cutoff point where when they see that, they're going to say, yeah, you've got an infection going on here, and this is how your body reacts to it. So this stuff is very practical. And if you're not interested in that, you could use it for other things. Can you use it for quality control? Right, you're making bolts. Right, you don't want the bolts to be all over the place. Don't you want them to be within a certain tolerance? You know, if it's a 1/16 bolt, I want it to fit 1/16 bolt holes, right? So what do you do there? Well, you measure lots of bolts, and these numbers will be tiny, but you can then figure out, is my machine producing bolts within the tolerance that I'm looking for? If you're into stock exchange, couldn't you find the average price of a stock and its standard deviation just by collecting data over, say, the last 100 days? And then couldn't you use that to predict when the stock is at its high level for its variation and when it's at its low level? And maybe you could use that to decide whether you want to buy that stock or sell it. So this idea of normal distribution can be used in lots of different ways. And that's the end of that section. Any questions about it before we move on to the next section? Are we good? Right. Oh, shooting space. I'm moving some windows around so I can get to the next thing I want to do.
I want to see you get like a 4-monitor setup.
Oh God, I'm bad with two monitors. Can you imagine how bad I would be if I'd be like watching tennis. I'd be going like this. No.
You look like an awesome hacker, though. You got your 4 monitors side by side, switching between them.
I'd be the worst hacker in the world. I've got so little attention span. Right, here we go. I finally opened up the window I was trying to find. So our next section is chapter 9. And here we go. Chapter 9 is called An Introduction to Sampling Distributions. Essentially, what we're going to do is some of the nomenclature, right? The jargon words that are used in sampling. And in particular, we're going to look at what is called a sampling distribution. So I want you to imagine that I'm interested in the average age of people who live in Bremerton. Now, I guess what I could do is I could do a census. Now, what I would do in a census is I'd find every single person who lives in Bremerton and I'd get their age, right? And if I did that, and I'm making numbers up, it's 35. So we would say that the mean of Bremerton is 35. Now, because that's a census, the symbol that I use for the mean is mu, right? It's pronounced mu, mu. And that is the symbol that you use when you're talking about the population mean. Okay. Now, while I was collecting the data on the mean, I also collected what the standard deviation was, and it ended up being 5. Okay, it ended up being 15. That looks more realistic. And that guy is using that letter, and we pronounce that letter sigma, and that's the symbol that we use for the population standard deviation. Now, if I did a census of Bremerton and I found their ages, then everything I could possibly want to know about the ages of people in Bremerton, I know. Couldn't I just find out how many 12-year-olds there are? And I'd be able to tell you that. Couldn't I tell you how many people were older than 70? How many people are less than 22 years old? I would know everything that I could possibly want. And censuses are great. Unfortunately, we very, very rarely do census. And there are lots of reasons. Financial. Can you imagine how much money it would cost just to do that? Right? Just financially. Practically speaking, it can be quite difficult. For me to do a total census of Bremerton, don't I have to know where everybody in Bremerton lives? Agreed? I mean, I have to go and find them, right? And I have to ask them. Do you know that's quite difficult, especially if you've got some homeless or transitory people, right? They don't have any fixed abode, right? How are you going to even find them? I mean, I guess you could try, you could cover Bremerton and then have people moving towards the centre and catching everybody like they were catching animals or something, but really very impractical. So we just typically just don't do it. Well, we know what we do instead is we get samples. Now, the kind of sample we're talking about is going to be the simple random sample. So even if the question doesn't mention that the sample is a simple random sample, well, we just assume that it is. And the reason is that that is the best kind of sample you can ever get. And so what I did, I'm pretending, yeah, is that I went and I got a simple random sample of 100 people who lived in Bremerton, and I got their age. And the sample that I got had an average age of 37. Okay, why is my sample not the real answer, 35? For what reasons would it necessarily not work?
Natural variation in your collected simple
Yeah.
random sample.
When you do a sample of 100 people, would you agree that you just sometimes get a couple of people who are a bit on the old side? It doesn't take many, right? There's only 100 people, wouldn't it? It would only take maybe a couple of old couples who are 75 and 80s, wouldn't it? And that could move your average a couple of years very easily. That's the drawback about a sample. When you do a sample, don't you only get a kind of snapshot of a number that hopefully is close to the right answer, but you're no guarantees, right, that the right answer is 37. Now, another thing, and I'm going to call this N1 and X1, is that I decide to do another sample of 100. And I get the mean of this new random sample of 100. Do you think that my second random sample is also going to be a mean of 37? No, there's no reason in the world it should be, isn't it? It's 100 totally random other people. It could be 36.5, couldn't it? And one more. So I do another one, and we'll keep the sample size as 100. And when I did it the third time, I ended up getting 36. And so statisticians knew this. I mean, it's just obvious that when you take a sample, in this case, a sample size of 100, you don't get the same answer every time you do another sample of 100. What you get is a distribution. Don't you get lots of different answers? And so they went and thought, theory, this is theory now. Suppose I took as many samples of 100 until I get bored. And then I collected all these samples and I made a histogram of them. And what they discovered is that the histogram has a shape that we are very familiar with. Do you recognize the normal distribution shape? And this is called the sampling distribution. That's the name we give to it. So I want you to think of this as lots and lots and lots and lots of different samples of 100. And that was 37, and this was 36.5, and that was 36. And I did it like thousands and thousands upon times. Can you imagine this distribution? And something very interesting happens. What do you think the mean of all these means would be? So where do you think the center of your sampling distribution would be in this story?
35.
It's 35. And so the mean of the sampling distribution is equal to mu, the population mean. Now that's kind of useful, isn't it? That we don't know that any given sample is a good answer, right? We don't know if we're a couple of years out or only 1 year out, right? Or 0.1 year out, whatever it means. We don't know for certain that this one particular sample that we did is a good or an average sample, right? But what we do know is the theory says that if you did enough of them, they come out about 35. That's good news, because that means then that sampling is a good way of estimating the answer. So if I was doing this sample, and that was the only one I did, when I say something like, my best estimate is the average age is 37. If my sample ended up being this one here, when I just say my best estimate is it's 36. Now, I'm not saying that the answer is 36 because it's not, but can I at least say it's probably going to be close to 36? Right? If you take a good random sample, it's probably going to be close most of the time. And do you notice that I'm using X bars here? So I might as well write that down here. X bar is the sample. The sample mean. And S is the sample standard deviation. Try to think of the word there. Wouldn't it be nice if I could find what the standard deviation of the sampling distribution is? I know what its mean is. Its mean is mu. I'll choose green here. So what's the standard deviation? Of the sampling distribution? Well, you might hope that it's sigma. It'd be really nice, wouldn't it, if it was sigma? But it's not. It's sigma over the square root of n. And you might think, where's this n coming from? N is your sample size. So when you do a sample of 100, the standard deviation of this is much smaller than the population standard deviation. And the reason for that is, if you just pick one person from a population, isn't there a lot of variation that that person could be? They could be anywhere. They could be an 80, they could be a 12-year-old, right? But if you take 100 people and you average them out, don't you reduce the variation because you've added up 100 and averaged them out? And so the reduction, right, in standard deviation is this. Now, what this formula tells us indirectly is that big samples are better for accuracy, which kind of makes common sense. If I did a sample of 1,000 people, right? If I did a sample of 1,000 people in Bremerton, wouldn't you expect that the mean of that sample would probably be very good estimate of the population, right? And the reason that is, if you plug in 1,000 there, isn't this a very small number? So the variation that you get in your samples will be quite small, right? Most of your samples will be darn close to the middle, right? Because the standard deviation is a tiny number. If you go the other way, suppose I only picked 10 people, right? I did a sample of 10, right? I went to Bremerton and I asked 10 people. Can you imagine that the standard deviation then would be a lot bigger? And so my estimate, the answer I got, I would be less confident in being accurate. So we know that random samples are good. What we also know because of this is that big random samples are better than small random samples. Big random samples will typically give you much more accurate estimates than small ones. And we can even quantify how much variation there would be. So let's put that together and see if we can come up with range of values. Wouldn't it be nice if I'll take this as my only sample? So let's pretend I only did that sample and I only got that one result, right? The average age was 37. Now I can say right now that my best estimate is that the average age is close to 37. But I want more than that. I want an interval of values where I am very confident the correct average, well, the correct, yeah, it's the correct mean age, I guess I'll call it that. Or Bremerton. Yes. So how do we create an interval where we can say in this interval, we're really confident that the right answer, 35, lives, okay? Well, what you do is the word very confident becomes 95%. Or it becomes 99%. Or it becomes 90%. So if I say I'm going to give you a what's called a confidence interval, that's the jargon that we use. I produce intervals like this. And if I wanted, which one do you want? Do you want to be 90, 95, or 99% confident? Which one do you?
What? Did he vanish?
Yeah, he's gone.
Am I the only one that says Celia's iPhone entered the waiting room? Because it looks like he just made me the host.
Yeah, you became the host.
Okay. how
When
do
he
I-
comes back, I believe it gives it to him again, but I'm not 100% certain on that.
Any of you guys had the problem that what he was writing was not like it was really low?
Everything was lagging. Yeah.
Yeah, I
It's
couldn't
been like
figure-
that since the start of the quarter.
Well, usually it is like that, but usually it loads after a second. Mine was just not loading.
Okay, I think it's fixed.
How long have I been missing for?
You only disappeared like less than a minute ago.
Oh, thank goodness for that. I was talking away quite merrily and I was asking questions and I was wondering why I wasn't getting an answer. So have you seen any of what I'm about to write down? In which case I'll give you a kind of heads up on what I've been talking about.
What I saw was where you were talking about the, you were writing, I'm very confident. Something.
Okay.
Yeah.
So we're here. Right. So what we've got right now is for a sample of 100, my best estimate is 37. But it would be nice if we could have an interval that we were very confident on. And in the statistic world, very confident ends up being 90, 95%, or 99%. There is another one which I'll not write down. There is a 99.9% confident. You know, so if you go that way, you pretty much are, yeah, I know the answer. So how do you get a confidence interval? And the question I asked, but you didn't hear it because we kind of crashed out of here, is which one of these do you want us to try? So any particular one of those percentages that you would like?
99.
99, because you just want to be really confident, right? There is a formula that we're going to show you for calculating a 99% confidence interval. It's X bar plus or minus the magic number for 99% is 2.56. This one is 1.96 right now. Well, anyway, we'll come back to these magic numbers. Can you just trust me? It's 2.56. I think it's 2.558, but 2.56 will do. Times what's called the standard error. And the standard error is sigma over the square root of n. So in this case, it's 15 over the square root of 100, which in this case was 15 over 10. So that's 1.5. Okay. So in my story, a 99% confidence interval was 37 plus or minus 2.56 times 1.5. Well, we just have enough time to do this, so it wasn't too bad. So here we go. 2.5 times 1.5 comes out as 3.75. Now, if you add and subtract 3.75, you will get your 99% confidence interval. If you take this away from it, you get 33.25. And if you add it to it, you get 40.75. Can you see that the interval then is that the real answer for Bremerton is somewhere between what, 33 and 40. And the real answer for Bremerton, at least in my pretend story, wasn't it 35? Did we nail it? Is the right answer in this interval? Now, let's talk a little bit for the few moments we've got. What does a 99% confidence interval mean? It means that, well, in English, it means I'm 99% sure that the right answer is in this interval. But doesn't that also mean I'm a 1% chance I got it wrong? And no matter what confidence interval you pick, isn't there going to be a percentage of the time you get it wrong? For instance, if I do that top one, won't my interval be wrong 10% of the time? And if I do this one, won't my interval be wrong 5% of the time? And in this case, it's going to be wrong 1% of the time. Of course, if you do something and you're wrong 1% of the time, don't people remember the one time you predicted it wrong and they totally ignore the 99 times that you got it right? Right? So when your manager comes and wraps your knuckles for you saying, well, you went and said it's probably going to be sales between this number and that number, and look what happened. It wasn't even anywhere near those sales. You know, what the heck are you doing? What am I paying you for? Well, it's not very helpful for you to say to your boss, well, the math that we use only gives me a 99% confidence interval, right? I'm going to be wrong 1% of the time, and darn it, it was today. But tomorrow, I'm going to be 99% sure when I tell you tomorrow's prediction, right? And whatever comes after that. So that's quite, I think that's quite a powerful thing. What that means now is that when I get a sample, can I not just predict what my best guess of the average is, but can I now give an interval with a certain numerical degree of confidence? I'm going to get it right 99% of the time. I think that's quite helpful to someone. Do you know this plus or minus thing? It's given a special name that you might have heard of. Some more jargon words. It's called the margin of error. You ever heard that term maybe in the TV sometimes or whatever? When they do elections, don't they say 52% are going to vote Democrat and the margin of error is 1.5%. You know, when they do that? Well, what they did there is they asked 100 or maybe more likely 1,000 people, right? And they got the middle number, right? The 52% guy. And then they just said margin of error plus or minus 1.5% or whatever. Now, here is a silly thing. It is possible to be 100% confidence interval. Would you agree that the answer is somewhere between minus infinity and plus infinity? Would you also agree that that is totally useless for practical purposes? So if your boss says, no, I want you to be 100% correct when you predict tomorrow's sales, right? I want you to be 100% right. If you told them it was that, wouldn't you probably get sacked for being a smart aleck? Right? You know, and hopefully managers or whatever the field is, they realize that statistics doesn't tell you anything for certain. Doesn't statistics tell you the best estimate that we can and kind of put some numbers on it? So isn't probability just a number that tells you how likely something is to be true or to happen? And aren't confidence intervals just a number or an interval of numbers that tell you your best guesstimate of where the thing you're looking for lives? Now, I made an assumption here, and it's a correct assumption because that formula is correct, that the standard error is sigma over root n. But to be able to calculate that number, don't we need to know what sigma is? But in real life, you don't know what the population standard deviation is, right? You don't know the mean, and you definitely don't know the standard deviation. So you have to do a little bit of a fudge. If I can't use that number, what number should I use? Well, I should use the standard deviation of my sample. I got to use somebody. And what does that do? Well, it tweaks these numbers. And what happens is that the formula I just gave you, which is this one, gets tweaked a little bit, and it's called the student t distribution. So we fiddle it in a different way. These numbers are fixed, right? So if you're using the sigma version, these guys are fixed, and they're the ones you're going to be doing. And a lot of this gets done with salt as well, but it's nice to see it by hand. And I think we have reached a very natural starting point.